Yeah, just to introduce myself, so I'm Tim Johnson. It's great to be here today, and thank you for the organisers for giving me the opportunity to come and speak today. It's my first time in Vilnius. It's also my first time in Lithuania as well, and it seems the community you have around this Build Stuff conference is very contagious. So I'm excited to meet and interact and connect with people over the next couple of days as we get to spend some time talking about coding and, in my particular case, science as well. So I'm here to talk today about some of the work we do at an organisation called Johnson Matthey. We're a company based in the UK. And I'm going to spend a little bit of time talking about what we're doing, why we're doing it, and how that links through to the coding solutions and the technological solutions that we provide to our customers. So the driving force through today is going to be talking about sustainability and how to make sure you bake that into your products and solutions as we move forward. Now, when it comes to being a chemical organization, one of the key things we have to think about is the safety of our employees and the work that we do within the space we're in. So I'm going to spend a little bit of time going over a safety moment. This is part of what we do at Johnson Matthey to make sure that we're constantly thinking about how to minimize risk when it comes to our employees, people, and planet. And that's obviously really clear when you're dealing with chemical processes. So if you have a chemical plant and something goes wrong, people can get hurt, can end up in fatalities, and people don't go home safely, and we want to make sure we're avoiding that. And this maps really well onto some of the technological stories that we see in the news today. I don't need to tell anyone about the potential risks of things like LLMs and data leaks that can occur, and this is a clear example that Samsung banned AI tools in April of 2023 because personal and sensitive data was leaked through ChatGPT, and that led to some embarrassment and potential loss of things like intellectual property. And in the chemical science space as well, we have this concept of the safety triangle as well, where a lot of things have to happen and go wrong before you get to those single big events at the very top, so those big serious injuries or fatalities at the top. And the way you deal with this in the chemical space is to ensure that you capture all of your unsafe acts and near misses as much as possible, with the aim that if you capture those and rectify them, then you get fewer and fewer of these big serious incidents that happen at the very top. And so my challenge to you today is to think how you, as an organization or in your own work or wherever you are, how do you ensure that you're capturing near misses to avoid those really big events occurring and mitigate against those as much as possible. And I'm happy to have conversations outside of the talk around this and how we can deal with this from a cyber and technology perspective as well. So I'm going to give a little bit of an introduction to the company itself, and this is really just to give you an understanding of why we're attacking some of the problems the way we're doing it. And I don't need to tell anyone in the room about some of the biggest challenges the world is facing today. I think individually, each one of these has impacted us to some extent over the last couple of years, be that climate change, resource scarcity leading to increased energy bills, energy insecurity similarly impacting people as well. And so there's a real need to make sure that we're driving towards a net zero world to ensure that we're protecting people and planet. And that's really what we're aiming to do as an organization and as a company. And you can't necessarily go out and buy a product that we produce. We don't sell to consumers, but what we do is help other companies achieve their net zero goals. So we are catalyzing net zero transitions for our customers and society, and really the leading companies in the world in sectors like energy, chemicals, and automotive, they depend on us to help them meet their goals in terms of decarbonization, harmful emissions, and achieving their sustainability goals as well. So we're an enabler in this space to provide chemical products and services to those organizations. To highlight that and give you a bit of a tangible example about the kind of products and services we provide, in your petrol vehicle or diesel vehicle, there is a catalytic converter in the tailpipe. 1 in 3 new cars produced globally has a Johnson Matthey catalyst in the back of the vehicle. So we are producing huge amounts of material that really drive towards net zero targets within society. And I'm going to put this slide up here as well, really just to emphasize why we're interested in this sustainability approach. So JM is about 200 years old. We're a UK-based company. We started off producing metals for the Royal Mint, so producing very high-quality metal and metal products. We've had a long time to build scientific knowledge as well. So we produced some of the earliest metal products that went into things like Faraday's early experiments in hydrogen. We've produced parts for the space rocket. The alloy that is in the standard kilo, which is locked in a vault in Paris, that alloy was produced by us, for for example. So a long history in this space. And we're number one or number two in the markets we play in. And that's really just to highlight that we really punch above our weight when you compare us to the size of the company of about 11,000 people. And we do that because we have a really solid understanding of the chemistry and the science that goes into the products and services we provide. And so we're able to punch above our weight and deliver products to our customers. And I'm just put the number there for the sales, less as to worry about the actual number, but to highlight that between 80 and 90% on any given year of that number comes from sales directly derived from products that impact the UN sustainability goals. So we don't just talk about being a sustainable chemical company, we actually sell products that help people achieve those UN sustainability goals in this space as well. And the last piece here, before we actually get into the fun stuff, really, it's just to address the essential transition needed for talking about net zero. So we're talking about transforming energy systems, decarbonising chemical products, driving down automotive emissions, and creating a circular economy. And we provide solutions in all those spaces to enable people to meet their net zero goals. So that's enough really talking about what it is, and hopefully this will give you some idea about the space we're playing in and why we're interested in what we're interested in. But why am I stood here, and where do I fit into this? So I sit within Johnson Matthey IT as a platform manager for our research and digital computing space. But my background is actually as a chemist, so I'm a lab-based chemist by training. I was mixing chemicals and producing products that we were then selling to our consumers. And I wanted to just put these two images up here because I think they're probably, for me, the two most consequential images I've probably ever produced. And it really led me on this path towards digital transformation. Now, that image on the left doesn't look like a lot, right? We've got a very old Battleship laptop in the back left corner, do not remove from lab written across the top of it. It's running some terminal, you can see there. But what we've got it connected to in the front here is an Arduino megaboard. And that Arduino megaboard is connected to a bunch of sensors that we've then connected to a reaction monitoring apparatus in the right-hand side there, the glass beaker. Key here is the entirety of this operation was put together for about $100 US. And this means we're able to share this knowledge with organizations in the third world, with schools, and people can build their own kits out of the technology that we put together and the code base that we put together for people to monitor the reactions that they're doing in the laboratory. And this plot just on the right, again, doesn't look very interesting, right? But what this demonstrates, if we look at the blue line here, is after about 4 hours, which you see in the line, we basically see no change in the reaction. And what this is measuring is the amount of cloudiness within that reaction vessel. And we use a sensor called a turbidity sensor, and we all own one of these. You may not be aware of it, but everyone has one of these in their washing machine. It determines when your wash is done, because there's no more soap left in the machine. So they're very, very cheap. They're commodity sensors, and we're able to plug this in. And what this allowed us to do was shrink the reaction time for this particular process from 60 hours, which was the proposed reaction time, down to 5. And you can imagine when you talk about energy, about waste, about time in the laboratory, all this stuff that feeds into the sustainability of a chemical process, it was all driven using this very, very cheap set of equipment to enable us to get some insights into our reaction that we didn't have previously. And this was really an eye-opener for me in about 2018, because what we're doing here is linking digital tools to physical science. And this is a massively important part of the process that we're now involved in really getting digital tools into the hands of our chemists and scientists. Now, these two individuals we're going to come back to through the remainder of the talk. And I really like to share this slide with my team when we talk about who our customers are and who it is we're actually delivering products for in the digital space. These two are actual engineers and chemists working at a pilot plant in the north of London. This is actually for recycling of battery materials. So you take your solid battery material, you do some chemical processing to it, and you're able to extract the valuable metals back out of your battery material. Now, these two are chemists and engineers, and at the end of the day, they need to turn a valve, press a button, flick a switch to make something happen physically in the real world. And when we're delivering products for these guys, internally or if we think about selling products externally, we need to make sure these guys have the right information at the right time to make the right decision to make the chemicals that they're interested in. And so the scope of today's talk really is about getting digital tools into the hands of scientists and engineers, how we do that, and the sort of mindset we approach this problem with in this particular space. So I'm going to give you a little bit of a chemistry lesson now. I promise you it won't be too much. But I just want to emphasize the simplicity of this particular molecule. This is methanol. You may have come across it. It's a chemical you can buy. It's very simple. It's simply a carbon atom and an alcohol group. It is the littler brother of ethanol, which is something we're all familiar with, normal alcohol. So it's simpler than ethanol in this particular instance. And the reason I put this up, and the reason I just wanted to demonstrate the simplicity of this particular molecule, is that in of itself, it's responsible for about 10% of the emissions from the chemical sector alone. So tiny molecule. You probably wouldn't know, you wouldn't have interacted with this in its raw form, but it's responsible for about 10% of the emissions globally from the chemical industry. And that's everything, right? That's drug discovery, that's oil refining, that's research and development, everything that's in that chemical sector, 10% of it comes from the production of this one molecule. And it's used in a range of different products, from paints, fuels, plastics, the construction industry, automotive parts, everywhere, right? And it's just really to highlight that methanol, in of itself, is a really important building block to products that we all use every day. You're sitting on, you're interacting with, you're using products that use methanol to some extent. And to highlight that, I'm just going to demonstrate just a few comments here where essentially methanol production has doubled in the past decade, and a lot of that comes from China. To put some flesh on that bones, in 2016, it took roughly 12 minutes for global methanol production to fill an Olympic-sized swimming pool. So every 12 minutes, you're producing an Olympic-sized swimming pool full of methanol. By 2050, when we reckon there's going to be 500 megaton of methanol being produced, that will be filled every 2 minutes. So every 2 minutes globally, you're producing an Olympic-sized swimming pool full of methanol. These are big commodity chemicals that are being produced. And this is a methanol plant on the image on the right. And this really just demonstrates the size and the scale of the problem we have here. You have large amounts of investment going into the production of these kind of facilities. You have not necessarily the greenest technology supplying those plants. And you have people who are very risk averse because they need to make sure their costs are being maintained as best as possible. And so we're in a situation where the newest generation of methanol plants is going to take some time to come online, which are using a much greener feedstock. And so we have to make sure we're providing the stock that is available to be able to produce methanol in as green and sustainable way as possible. If we can't do that, then we're in real trouble when we look at the size of the industry as we move forward. So if I think about these two individuals again, these chemists and these engineers, maybe they run a methanol plant, maybe they're responsible for making sure that it functions correctly. I, as an engineer or a chemist in this instance, am really interested in making sure I get the right data and the right information to make the right decision about my facility and ensure that I'm in a position to generate this particular product in as green and sustainable way as possible. And so we provide a web app. This is called JM Levo. This is essentially a web portal that our customers can access. And what this does, using expertise internally and the development teams that we have internally as well, it can pull together data and display that data for our customers to enable them to make the right decision about the plant and the chemistry that they're doing at any one time. You can see here we've got things like loop carbon efficiency. I don't know what this means, right? This is all gibberish, but it's important for the individuals who are actually running the plant. This is important information to be provided to them so they can make the right decision at the right time. And we can link this through with modeling and with other metrics as well. We can see here things like reactor sizes and understanding gas flow rates and all sorts of things, right? This is all stuff that's relevant for individuals in that industry, and we're providing this to them in a single web portal that they have access to. So when it comes to this particular product, JM Levo, we are able to provide a solution to enable individuals to view plant data, to visualize their metrics, to optimize production, and more importantly, and we're going to talk about artificial intelligence in a minute as well, at the end of the day, especially in these large chemical sectors where you've got a lot of plant and a lot of individuals who might be impacted if something were to go wrong, you can access expertise as well from Johnson Matthey to help you solve problems that you might have as well. And in this particular instance, we've got about 100 licenses and about 60 million tons a year of methanol is produced using technology that we provide in this particular space. So really is a product that we can wrap up and supply to enable those chemists and engineers to produce their chemical product as sustainably as possible. So linking digital tools and physical sciences again. So let's just reflect now, if I were a chemist or an engineer running a methanol plant, I now have all this data at my fingertips. I can optimize as production is going on, and I'm really in a position to produce chemicals as sustainably as possible in this space. So that's just a little bit of the sort of traditional sort of web portal stuff that we're able to provide. But it can't be a technology talk in 2024 without talking a little bit about AI and how we leverage AI to solve some of these problems as well. And we've got a particularly interesting set of problems here when it comes to solving scientists' problems with artificial intelligence as well, because often those problems are very nuanced, and you need expertise to be able to derive proper meaning from them as well. So to give a bit of background here and a bit of context, we spoke a little bit about Johnson Matthey JM Levo as a product to enable people to understand plant data that's coming through. This is, on the left-hand side, this is a shot from ChatGPT I collected about a week ago. And this is something we're all familiar with, right? You ask a large language model like ChatGPT, tell me about something, and it very confidently tells you a load of stuff which is absolutely incorrect, right? Talks a little bit about battery materials, that's not true. Talks a little bit about cathode nanomaterials, not true. Battery materials, they said, for electronic vehicles, not true. Talks a bit about sustainability, so it's getting there a little bit there. But really, it's just completely incorrect, and confidently incorrect as well. And it was really, it sort of changed my perception on this, was a conversation I had at a Microsoft Developer Day about this time last year. And it was that large language models essentially hallucinate all the time. And I don't mean that they are incorrect all the time. That's not true. They generate incorrect data, but even when they are correct and the output can be mapped against reality into something we think is correct, it's still a hallucination. There's no difference. It's a statistical determination of what the next word in a sentence should be. And we need to be really mindful when we provide solutions to chemists and to scientists, to engineers, that we have an understanding of the impact this can have when dealing with chemical problems, chemical systems that when they go wrong, they can have real world implications. So we have to treat off-the-shelf systems with a huge amount of skepticism. And even when they are trained on the chemical data, Microsoft has a really great product called Microsoft Quantum Elements that has a chatbot in it that's trained off chemical data. Even when we have off-the-shelf systems like that are trained on chemical data, they can still be wrong, and the impact of relying on these too heavily can be massively detrimental. And so you need to make sure you've got expertise throughout this entirety of the process. We need to make sure that when the correct answers are found, and more importantly, when we deal with publicly available or even privately available AIs, they're often trained on public knowledge. And a company like Johnson Matthey has a huge amount of information internally that isn't publicly available that these models have never seen and won't see, because we need to maintain that, sensitivity around intellectual property, for example. And just to sort of further highlight this as an issue, this is our main research facility just outside London in the UK. We've been there since about the 1960s, and we had a bit of the talk earlier today, the keynote at first thing this morning, was talking a little bit about how we've been through many of these different transitions from technology over time, right? Where we are now, we would not be able to guess where we would have been 20 years ago, for example. And so you can imagine a scientist here in the 1960s using pen and paper, maybe using open flames in their laboratory, right? Not really worried about safety goggles or glasses or lab coats, right? How that's now changed and where we are today with a very high-tech, very mindful and switched-on group of individuals who are really interested in making sure they're able to do the science in the right way and utilizing all these digital tools that we have access to. So if you think about the paper trail alone in a place like this is extraordinary, and the amount of data that's maintained there and locked in is really quite extraordinary. And so we need to make sure we're in a position to utilize and access that data and get a return of investment on that data as well as we look to the future. So if I think about our chemists and our engineers who are sat there now in that research facility, they want to have timely access to their data, they want to make sure it's correct, and they want access to domain-specific knowledge that they have access to rather than anyone else. And so the particular aspect of AI I want to talk about today is ontology management in this particular instance. And what that essentially means is linking words to meaning in this space. So we can have some really nice examples of this, and one that impacted me quite heavily in my past life was we used a chemical called BTC. It's an acronym, BTC. Now, BTC is also the ticker name for Bitcoin. And so I had many emails blocked by our spam filter because it thought I was talking about the price of Bitcoin and not the price of a particular chemical that we were interested in. And this is a really simple example, but you can imagine over the entirety of a domain like chemistry and chemical sciences, there's a lot of these examples and a lot of cases where you need to link meaning to specific concepts. And so we build on tools that enable us to build taxonomies and ontologies to enable that. And key here is making sure that we use our crowdsource facilities, so we use our employees to build these taxonomies and ontologies together. That means they're very domain specific, and individuals can access those ontologies and taxonomies for their specific area. And if we couple this with things like AI-powered OCR, which is really very good now, we're able to digitalize a bunch of the physical notebooks that we have in a site like the one I just showed you, and we're now able to search that and interface that through an API-first approach to ensure that chemists and scientists are in a position to access the data when they need it, and it's as accurate and as relevant to them as possible. And so really what we're doing here is mixing AI and chemical-specific knowledge to pull together meaning from an awful lot of data sources that aren't necessarily publicly available. So when I think about our chemists and our engineers, right, they're happy. They've got access to this large wealth of information, internally available information, that they're now able to access and interface with through things like large language models and through natural language. So they're happy in that regard, and they get the right information at the right time to make sure they can do chemistry in the ways that minimize impact on people and planet. The last piece I really want to talk about today is around chemical modeling, and we saw a little bit in the keynote talk earlier today about chemical modeling, about quantum computing as well. And I just want to touch on a couple of those key themes because I think it's massively important here as well. So why are we interested in modeling systems? Why are these two individuals who are in a manufacturing plant in the north of England, in north of London, why are they interested in chemical modeling? And it really comes down to sort of four key pillars here. So when it comes to chemical modeling, you're in a position to save time in the laboratory. That's key here. And when we think about sustainability, saving time in the laboratory, reducing the use of chemicals, not having to use energy to run experiments is massively beneficial in this particular space. And also, we spoke a little bit about health and safety as well. The easiest way to reduce that triangle is to ensure that you don't expose our workers to chemicals in the first place, right? If we can run experiments in the computer, we reduce the risk of exposure to our individuals, and it reduces that risk completely in that particular space. And we work with some particularly nasty chemicals in the research side, things you would not want to be exposed to in everyday life and things we have to put a lot of effort in to make sure people aren't exposed to. And you can also explore the synthetic space very effectively as well. So you can jump in, produce materials that maybe aren't physically possible, or we don't yet know how to make them, and you can explore them and see where you want to focus your research and development time. So modeling allows for more agile science while protecting people and planet. That's really key when we talk about sustainability. And so we do a lot of work with the physical and chemical modeling group based within our R&D team. And really key here, I just want to highlight, is that when we talk about chemical modeling, it's the whole gamut, right? We go all the way from quantum mechanics, which is single atoms on a surface, for example, to molecular mechanics, to fluid dynamics, all the way up to the output from a methanol plant over many years or many days, similar to what you saw previously with the web portal that we showed. So we're modeling all these systems, we're doing it constantly, and we're using a lot of internal expertise to make sure we're able to do that in the right way. So we gain insight, we can characterize these materials, we can screen, which is massively important in this space, and we're also in a position to predict the material behavior as well, which is really key when you want to make sure that the thing you are going to make, that effort and that time and the energy you're going to put into making a product at the very end is the right one, because we predicted it So one of the things we look after in the team is our high-performance computing cluster. So we saw a little bit about supercomputers earlier, and this is the tooling that we give our scientists. So for those who aren't familiar with how high-performance computing works, essentially a user will have an idea for a calculation they want to run. They will then access the high-performance computing cluster, split that job up into multiple different jobs, and then submit that over a number of compute instances. And that enables you to get calculations done much, much faster. We link that up with storage, and you can imagine what this would look like in an on-premises environment where you basically have a large cluster sat there constantly chunking numbers away. And indeed, that was how this was done. Traditionally, if you're a university or a large research organization, you would have an on-premises cluster somewhere in the basement, gate-kept by a individual who would spend their time looking after and nursing the computer through all sorts of calculations. And in around 2019 or so, we moved over to using cloud-based approaches in this particular instance. So we are now completely based in Azure for our high-performance computing work. That's enabled us to do a number of very important things. Firstly, it's given our scientists and engineers access to the best possible compute at any given time. They have the bleeding edge in this particular case. And also, if you had an on-premise system, you'd have to submit your expenditure request. You might get a cluster that is over-performant for an amount of time, maybe 2 years. It's over-spec'd. It's then just about right for a year, maybe 2. And then as the technology changes, you've then got a cluster that no longer functions correctly and is not fit for purpose. And you then have to submit another request for more expenditure. And that can be a very difficult and troubling process to go through. And so moving completely onto the cloud, onto a model where we rent cloud space essentially to do these calculations, has really helped us democratize and push this kind of approach across the entirety of the organization. And so cloud HPC is really important, and it is an enabler across multiple sectors in this particular space. And I could sit here and talk to you about capacity and capability. I don't think that really needs to be explained too much here. That the more compute you have, the closer your models get to reality, and the more insight you can gain from your chemical system. But key here, and potentially for the individuals in the audience today, is around democratization. So we can run more jobs. It's accessible across the entirety of the organization, and it's no longer gate-kept by individuals in a specific area. We're able to put a service wrapper around this and deliver it as a service to our chemists and our engineers. To put some flesh on that bones, I just want to talk a little bit about a publication we put together in about 2018, just to demonstrate the real change that we've gone through in this particular space. So this, again, it's less important about the chemistry here, but essentially we wanted to model some physical properties of the chemicals you see there in the bottom of the slide. This work was conducted in 2018 on our on-premise system, and it took about 3 months to run this particular calculation. It was very, very computationally expensive to do. The same calculation today on the cluster that we provide individuals would take between 2 to 3 days. So it's been a massive upscaling of the kind of science we can do and the speed of that science as well. So HPC really should be seen as an enabler, and it really allows insight to be gained much faster. And when we're talking about doing chemistry as sustainably as possible, this all helps. We're reducing the impact of our research and development efforts. We're producing the next generation of products and services for our customers, and we're doing that in a way that is fast and agile, and we're able to deliver that to our scientists and our engineers internally. So I asked a little bit about why you'd be interested as a chemist or an engineer. Why would you be interested in chemical modeling? Hopefully that sort of demonstrated it, right? We can reduce risk, we can reduce time in laboratory, energy savings, we can be really efficient with our time and our time in the laboratory. So they're happy, right? They're in a position to get the answers they need and the data they need as efficiently and sustainably as possible. But if there's one thing we know about these kind of customers, right, about chemists and about engineers and scientists in general, is they always want more. And it's why I was really excited to see the talk earlier today where we spoke a little bit about quantum computing. And I want to spend a little bit of time today just touching on quantum computing and how that maps onto the chemical science space, because I think that kind of work is massively important as well. I also want to demystify it a little bit as well, because I feel often when we put phrases like quantum computing, and you saw the chandeliers earlier, and it looks very, very complicated and otherworldly and sort of fantasy-like. It's really important that we can map that onto reality and the kinds of products and services we can provide in this space as well. So I've got two images here. The first one on the left is a plot demonstrating how classical and quantum computers change when it looks to time to solve versus the problem size of your particular problem in this space. So obviously, for small problem sizes, you have classical computers are much more efficient in that initial space. There is a crossover point where quantum computers start to become more efficient and can solve things faster. And actually, classical computers, you see this hockey stick effect here. The time to solve some of these very intractable problems is sort of heat death of the universe levels of time to solve, basically impossible by current classical computers. And that's where quantum computers kind of come into their element for these very, very complicated systems. And I mentioned I wanted to demystify a bit, and then I put on this AI-generated image of what quantum computing is. But it's very difficult to pull together this when we want to map it to reality. But when we talk about quantum computers and how quantum computers function, it's incredibly similar to how chemicals behave in the real world. So when we talk about qubits and we talk about superpositions and we talk about all this stuff and superpositions of the entirety of the computer, that is how atoms arrange themselves in reality. And so if we can utilize this technology, we're in a really strong position to model reality as closely as possible. And that gives us models that are much better, much closer to reality, and means that we're able to be much faster when it comes to developing chemicals or new areas for sustainable chemical purposes. And to highlight really what we're trying to do to make JM quantum ready, we're engaging with national organizations like the National Quantum Computing Center. This is an image taken of a hackathon that happened this year where several hundred academics, computer science students, and industries, as well as quantum computing suppliers as well, all came together in England to run through some industrially relevant problems. And JM was an industry sponsor for this, and we provided problems for the students to work on. In this instance, what we were looking at was actually it was a number up to 300 or so different variables that had an impact on a chemical process. And we developed an algorithm during this 2 or 3 days to enable us to effectively narrow down those 300 or so variables into a much smaller number to enable us to produce a model that had much better predictive performance than we had before. And key here is that we're mixing quantum computing to do that rationalization of variables down from 300 to a subset of, I think it was around 10, and then passing that off to classical computers to do the remainder of the work. And so we're linking up together classical and typically cloud computing processes with our quantum computer, so we get the best of both worlds. And we're able to demonstrate the value of this there as well. So through external engagements, through training and through recruitment, we're really in a position to drive forward utilizing this in the chemical sector, again, to produce products, chemicals, and services as sustainably as possible. So I'm just going to throw some acknowledgements up here. Thank you very much for spending time today listening to me talk about sustainable chemistry. If we've got time for question and answers, I really just want to leave this with you, which is what can you do in your work to help drive sustainability? We all work on products and services, but how can we make sure we're embedding that thinking about making things as green and sustainable as possible across the products and services we provide? And also, just as an aside as well, we are actively recruiting in Lithuania. We have a Lithuania Global IT Hub standing up at the moment, and we have a booth and a stall here today that is also available. So do come and chat afterwards. Come and discuss things about the chemistry and the science. Let's talk about sustainable chemistry. Let's talk about doing that safely and what digital tools we can use to do that as safely and sustainably as possible as well. And yeah, as I say, let's have those conversations about sustainability and how we can use digital tools to do that. So thank you all for your time.